Hello, Assalamualaikum. My name is Noratika Syahira binti Uyuk from Group 3. We want to present our report for Experiment 7, which is about estimation of heat capacity and entropy generation. So this is our group member that do this report for Experiment 7, which is me, Noratika Syahira binti Uyuk, and Muhammad Adam Luqman bin Razali. Now, I will explain about the introduction for this experiment. The heat capacity is defined as the amount of heat required to raise the temperature of a mass substance by 1 degree Celsius. The specific heat capacity, which is Cp, is amount of the energy needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius. As you can see the formula, which is Cp equals to a mass of water times with specific heat capacity for water and delta T for water divided by mass of solid times with delta T of solid. So the heat capacity can be measured by using variety of calorimeter and using the formula third law of thermodynamics. There are variety of calorimeter which are differential scanning, isothermal micro, titration calorimeter, accelerated rate of calorimeter. We use the simple calorimeter, which is just consists of a thermometer attached to the metal container full of water suspended above a combustion chamber for this experiment. So the specific heat capacity is important to determine the entropies of materials. The entropy generation is the amount of entropy which is created generally during irreversible process by means of heat flow through thermal resistance and the others. According to the increased entropy principle, the entropy generation can only take positive value. So for this experiment have two objectives, which are first to estimate the heat capacity of different metals provide, and the second is to estimate the entropy generated when these metals are dropped in a container containing water. Okay, now I will explain about the theory for this experiment. The amount of heat needed to increase a body temperature by 1 degree Celsius is known as heat capacity, like I told you the introduction part. As two bodies with differing temperatures exchange the heat, the amount of heat lost by warmer body equals to the amount of heat gained by the cooler body, and an intermediate equilibrium temperature is achieved. This is valid as long as no heat lost to the surrounding. A heated solid known as mass, which is m, and temperature is lowered into a calorimeter containing non-mass m2, which is cool water that we use in this experiment. After that, then only the equilibrium temperature is determined. As you can see, the heat lost by solids must equal to heat gained by water, which is at equilibrium state. So the equation we use is the mass solid mass times with specific heat capacity for solid and the delta T for solids equals to mass of water and specific heat capacity for the water and delta T for water. So we need to calculate the specific heat capacity for the solid. Okay, for this slide, it shows the systems or its environment entropy shift may be negative, but overall entropy production is still positive, like I said before. A process must proceed in the direction that complies with the increases of entropy principle. For the entropy generation must greater than 0. The entropy generation, which is a measure of the magnitudes of the irreversibility present during the process. The entropy generated during this process is determined from the temperature final for the solid equals to temperature final for the water equals to the which is mass equal to the temperature final. So for the solid and the water, we use the same equation, which is delta S equals to mass times with specific heat capacity, and the times with Laurent temperature final divided temperature inertia, which is we use the value for solid and the water. After that, we calculate the total entropy generation, total entropy, which is equals to delta S solid plus delta S water.
For the methodology, we have 11 steps to follow to run the experiment. Which for step 1, the Cooper method is being weighed using the weighing scale and then being recorded in table 1. The step is repeat for aluminium and iron steel. After that, 18 ml of water is pure in the first beaker. First beaker. First beaker. Once hash is reached at 80 ml, the water is heated using the hot plate. As for step 4, the copper block was attached with a metal spring. For the next, the copper block is lowered inside the heated water until fully submerged. The copper is allowed inside the water until the temperature reach 80 degrees Celsius. The temperature of metal is assumed temperature of water. 80 ml of water is filled into the second beaker. Then the initial temperature of water is measured by thermometer. The temperature of water in the first beaker is measured by thermometer. Next, the temperature of water in the first beaker is reached 80 degrees Celsius. The copper block is taken out from first beaker by metal spring and immediately transferred into second beaker that contains 80 ml of water. Next, the beaker is covered by aluminum foil to minimize heat loss to the surrounding. The temperature of water is recorded for every 10 seconds until it reaches the constant temperature. The water is straight throughout the process to ensure even heat distribution. For the last step, the steps from 1 to 10 are repeated for aluminum and iron steel. Next, for the result, these all tables show the result we are obtained from our experiment when we are running the experiment. We have the time for initial temperature which 0 and until 100 second, and we have temperature for every steel, which is aluminium, copper and iron. From that, we can obtain the initial temperature of metal, equilibrium temperature, which is the last temperature we obtain from the experiment when it's constant temperature, and the temperature change of the metal and the temperature change of the water. Next, for the calculation, these all equations show us how to calculate the specific heat, which is specific of steel equal to mass of water, specific heat of water, and temperature change of water over mass of steel and uh, change temperature change of steel. We also can calculate the entropy change, which is entropy change of steel equal to mass of steel, specific heat of steel, and ln T2 over T1. We can obtain from the table. Also, we can calculate the facility error for every specific heat for the experiment each meter. We also obtain the mass of water, aluminium. We also calculate the mass of water, aluminium, copper, iron, and obtain the volume of water. And we can search the specific heat of water, which is 4.187. Next, for the calculation also, we for this table show the temperature, every temperature, initial temperature, final temperature, and temperature change for metal and water also was converted into the Kelvin temperature, Kelvin unit. For next, for that data, we can calculate the theoretical specific heat capacity. Theoretical specific heat capacity for aluminium, copper, and iron. We can search find the theoretical specific heat capacity, and we can calculate the experiment specific heat capacity from the table we are obtained from the table, and also we can calculate the enthalpy change. And the last, we can from the theoretical value for specific heat capacity and experimental value of specific heat capacity, we can calculate the percentage error for every metal we are doing the experiment. That's all from me. Thank you.
Now I will continue with the discussion for this experiment. The discussion for this experiment, we have three to discuss, which is firstly we need to discuss about the source of error and the method to minimize the error. First, the error we have is the parallax error, which is we need to avoid parallel error. The line of vision should be perpendicular with the scale of the thermometer. Second, we do not cover the calorimeter completely. So for that, we should cover the calorimeter completely because to avoid the heat loss to the surrounding. The third error, we do not clean the surface of the metals before the experiment start. Because of that, we must to clean the metals, which is to avoid any materials attached to it that can disturb the temperature reading. The last one is we lack of time to take the reading of temperature. Because of that, we should do the repeated experiment for each metal to get the accurate data. The second discussion is about justification on the importance of stirring the water in the container. The importance of stirring the water in the container is to ensure that the even heat distribution throughout the experiment. But do not stir the liquid in the calorimeter vigorously, because the vigorous stirring does cause some increase in temperature. The third discussion is justification on the importance of transfer the hot metal quickly into the water. The importance of transfer the hot metal quickly into the water is to avoid the heat transfer to the surrounding and to get a more accurate equilibrium state. So, lastly, the conclusion for this experiment is about the different substance will absorb heat at different rate due to the various structural factors. The amount of heat lost by the warmer body equals to the amount of heat gained by the cooler body, and the intermediate equilibrium temperature is achieved. This is valid as long as no heat is lost to the surrounding. From the experiment, the heat capacity for aluminium, copper, and iron is 0.1989 kilojoule per kilogram Kelvin and 0.194 kilojoule per kilogram Kelvin and 0.275 kilojoule per kilogram Kelvin respectively. Besides that, the value of total entropy generation cannot be negative, like I said before, and thus the total entropy generated for aluminium, copper, and iron, we get 0.0021 kilojoule per Kelvin and 0.0063 kilojoule per Kelvin and 0.0085 kilojoule per Kelvin respectively. The total entropy generated for copper and iron is greater than aluminium. For the experimental result is different from the theoretical values because of some errors that might be happen during the experiment is conducted. That's all from us. Thank you.